this new rally. Because you know why? Today, we're going to delve into the deep depths of special relativity. So I know that one of my students, Albert precisely, has already made lectures on this. But deep here, we're not going to go into the math. We're going to understand. First, we're just going to give you an example. So, say that you take a particular object, maybe a crowbar-shaped one for preference, and then you gripped it by this black dot, and then you spun it around. Pretty dangerous unless that crowbar was soft. So I recommend you use a soft crowbar instead of a hard one. Anyway, now it will look to you like the whole thing is rotating. So it will look to you as if the crowbar-shaped thing is rotating. But however, somebody else watching from the perfect angle may see something like this, where the crowbar is facing at them this way, and then it somehow turns around like this, and then it goes the other way. So now you have one perspective, the perspective that you see, and then you have another perspective, the perspective that someone else watching would see. Notice who has a bigger pupil. Anyways, that doesn't necessarily mean that the person watching has to have a bigger pupil than you, but anyways, person A, so you, as the person doing this and watching this, have one perspective, while another person seeing at the perfect angle may see another perspective. Question is, who is right? Well, the answer is really no one or everyone in that matter. Everybody here is right. Both perspectives are right. So, special relativity sets to change these kinds of questions. Special relativity sets to answer these kinds of questions. Not only special relativity, but just relativity in general. Now, we're going to look at something now. Special relativity, not general relativity, relativity in general, not the subject, can be split into two separate parts. Now, those two parts consist of one, things that do change, based on perspective. Things that do change based on perspective, and things that don't change due to perspective. From now on, I'm going to call one the dependent variable, and I'm going to call the other the independent variable. The different thing are based on your perspective. Thus, they are a dependent variable, dependent on your perspective. Same applies for the independent variables. Do you want to listen to this lesson, Mr. Alex Rodriguez?
Yes.
I haven't seen you in a long time, but
Yes.
seriously. So anyways, we already seen an example of what is different and what doesn't stay the same. But what does stay the same is a little bit trickier to find. You can learn from this. After all, this is relativity, so Einstein knew this kind of stuff. So now, relativity is actually not as hard as it may sound to be, because when it's taught, they throw these scary equations at your face with no true algebraic meaning. So it seems that you are intimidated by these kinds of equations, that you have little intellect that to recognize. And yes, for one, I was surprised about them too when I first discovered relativity, which was like 2 years ago. And it was pretty surprising to me how such a complicated topic back then could be transformed into such a simple topic to understand right now. So, anyway, we've already seen what's different, but what's the same is a different story. Get it? So now the independent variable, you may think at first that position is actually absolute. It can't change. But even Galileo's relativity disproved that. Long before the realms of Einstein, Galileo actually contributed to relativity too. But they had no idea about time. But we're going to talk about time later. Anyway, even Galileo, that guy from the 16th century, he disproved that fact. Because let's say that you take a graph where you have your x and your y. We'll call your perspective the perspective of person A, x-A, y-A. And now we're going to make a certain point that we'll call x. And then we're going to take a certain point that we'll call y on your system. So now, that's the point you have. And it has coordinates x, y. However, let's say that somebody near you is also looking at that same object and maybe has a different perspective of it. So now we have two, since their frame of reference is placed at a different point from you, they have thus a different perspective, meaning that their take of things is different than yours. So this is actually, at the y prime we'll call it, and x prime we'll call it. So now, a noticeable thing to see is that So anyways, I'm going to, you know that x prime and y prime are definitely different from x and y. So you may be thinking, who is correct? And that again leads you into the loop of this little thing. So that means that position is not absolute, but rather relative. But however, what happens when you see 2 points is rather intriguing. So let's erase this crowbar example and the word relativity, and wish I could have a napkin instead of this crummy expo eraser, like 5 years older right now. I have to erase so thoroughly. Okay. So now, anyway, what happens when we add 2 objects to the scenery? So we're going to take our perspective, x-A, y-A, and then we're going to take a certain point, let's say over here, and we're going to call this x1, and we're going to call this y1. Now, we're going to take another point somewhere maybe here, and then we're going to call this, oh no, that's above the axis, maybe here. Now this is x2, and then this is y2. Now we know that the distance between them via the Pythagorean Theorem, but that's a little complicated. So let's assume that they're at the same y level, and they only differ in the x direction. That makes the distance between the two x2 minus x1. Now, if going to review that in a few minutes right now. So now, this is going to be x2. This is going to be y2, x1, y1. So now, what you have to do is via the Pythagorean Theorem. The distance between these 2 points, and we'll call that d, is going to be equal to the square root of the sum of the squares of both of the legs. No, not the legs as in this sense. The legs as in this sense. So now, anyway, we're going to have this first side is obviously going to be x2 minus x1. And the second side is going to be y2 minus y1. So now we can see. Oh wait, that's a problem. Sorry for the inconvenience. It's actually y1 minus y2. You can't have a geometrically negative distance. So y1 minus y2 is going to y1 minus y2 is the y. So we're going to have y1 minus y2 squared plus x2 minus x1 squared. Now, if you can calculate that, that gives you something like this, I believe. Y1 squared minus 2y1 y2 plus y2 squared. And then we do repeat, rinse and repeat. So x1 squared minus 2x2 x1, and then plus x1 squared. No, x2 squared. So now, I'm pretty sure there's no way you can simplify this further. This is horrifying. So maybe it's just better to stick to the shortcut. You know what I'm saying? So this equation is the equation for the distance. So now that we've got that more complicated scenario covered, we're going to go back to the simple scenario. Now, we know that this is going to be x1 comma y1. And let's assume that this is at x2 comma y2. We've already, x2 comma y1, we've already covered the part where it isn't. So now, x2 minus, we're going to have, the distance between these two is the x1 minus x2. That's the other way around. Because x1, x2 is actually greater, sorry. So x2 minus x1. So that's the distance between the two. Now, x2 minus x1 is the distance between the two. So let's say that we take another coordinate plane, like this one, where there is xb and this is yb, and these are at different points. So now, now that these are at different points, we have to recognize this as a different thing altogether. So y prime, and we're going to call this one x1 prime, and this one x2 prime. The amazing thing is, it doesn't matter what their positions are. The distance between the two is still the same. It's evident. So that means that x2 prime minus x1 prime must be equal to x2 minus x1. So, and now, that's the equation we've got in. So now, this scenario is a little too complicated to cover for now. So, we're going to move on from it. Ooh, okay. So now, let's just do the thing. And now that we have that covered, what do you think is absolute now? Sorry, I have to rephrase that. So anyway, we thought that the distance was absolute, but what Vsauce music will kick in now. Just kidding. So now, let's say that we have 1 point at x1 and the other point at x2, and now they must be separated by a distance of x2 minus x1. Now, let's say that they are to 1 tick mark apart. That means 2 units apart. So 1 unit, 2 units. However, what if I change to a different unit? Made these more frequent, the tick mark more frequent. Now we would have something different. Most likely this. We would have 1 unit, 2 units, 3 units, 4 units, which would go like this. So now we have now since we've split them into parts, we now have one from the length of 2 units to 4 units somehow. But how? Well, to change it back, what we can do is do this. Let's say I jump out the fire escape and then rip off a branch from a tree. That I rip off a branch from the tree, and then for my luck, that branch actually decides to be the exact same length of 1 unit. So now that means that whatever I do, this branch will be these points will be 2 branches apart. 2 tree branches that I ripped by jumping out the window apart. So now, that would work even with different units. As if we take the stick down, the stick still measures as the same thing. So the stick's same length would be provided here, which would mean the stick's length would go from 1 unit to 2 units. However, x1 and x2 still are 2 sticks apart, as if you divide 4 by 2, you get 2 sticks. Or more precisely, 2 sticks that I ripped from a tree by jumping out the window. Or 2 stir-fried bajatwa. So, anyways, an intuitive way to see motion and action on one-dimensional planes like these is to graph them. Yeah, graph them in space-time diagrams. The space-time diagram may seem intimidating, but hey, it's just your regular coordinate plane, buddy. Nothing to worry about. So, now your regular coordinate plane is actually only like the regular graphs you have. What you have to do, what you have to do is, there is t on x-axis, there is t on the y-axis, and x on the x-axis. So pretty funny, huh? Okay. So anyway, x will be the graph of the motion of an object over the x coordinate. So now t will be its motion over time. So let's say that I move my fist like this to smack the face of my students. That would look like a sine wave because I'm waving my fist in continuous cycles. like this. So when Mr. Rodriguez, listen up. Okay, when I punch my fist, when I move my fist to punch the face of my students because they didn't get their quiz right, my fist is actually moving through the x-coordinate plane, which can be graphed on the plane by sine wave. Because if you actually look, while I move my fist up, it actually follows the same pattern, the same rhythmic pattern. So, sorry for our YouTube video viewers, but anyway. Okay, so sorry viewers, we're back on track. So anyways, if I move my fist in a sine wave to punch my students, while moving it up, you can actually see that it synchronizes with the space-time diagram. However, this is only for one-dimensional motion. You may ask, how do we graph two-dimensional motion? Well, it gets a little more complicated, and going after that is impossible. You may ask what I mean, but witness what you see here. This is the X, this is the Y, and this is not the Z, but the T for time. So this is how to graph two-dimensional motion. And it's pretty intuitive, but it can get really messy really quickly. So people often don't use this much unless they are really good at illustrating this or they're using a computer to do so. Now, illustrating the three-dimensional motion is fully impossible as we know it, because that would require another spatial dimension, as well as time being its own spatial dimension in itself, which is fully impossible in our universe with its three dimensions. Seriously, you gotta get more dimensions, universe. Anyways, now, final thought on this is that is not my final thought on this. So, it actually kind of is, because this is the last thing I have related to the subject, because space-time is very easy, although it sounds intimidating, it's actually very easy to graph, and is a very intuitive way to graph the motion of the objects over time, like the motion of my fist to punch my students, or the motion of this eraser moving in a circle, etc., etc. Now, the last thing I want to say is, bye everyone.